So we are now going to discuss in this part 4 some very basic example of bifurcation based on the classical Hopf bifurcation. So we consider here a dynamical system x dot equal b that now is going to depend on a parameter lambda. It can be a set of parameters, but for simplicity, let's suppose this is just one real parameter. The notation can also be b lambda of x. And so we know that there exists a solution for each lambda, as we have seen from Cauchy theory, t going to the mapping x lambda of t. And so we are interested in what happened when lambda, now we have here lambda, which is a real number, varies. So what can happen to the dynamics to the ensemble of recurrent set? And for this, I would like to take the very elementary and fundamental example, which is called the Hopf bifurcation, where you have a dynamical system in dimension 2, x, which can be written in polar coordinate, r exponential I theta, where theta dot equals the constant, let's say 1, and r dot is going to be r, let's say a constant beta plus r squared. So now what happened to the recurrent set when beta is changing? So this is beta, so beta here is going to be equal to alpha. Well, so when beta is strictly positive, as you can see from this, the second equation 2, the only critical point is r equals 0. And since r dot is strictly positive, and you can integrate directly this equation, you can see that r of t, the trajectories, tends to infinity as t goes to infinity. And this is really well represented in this cartoon here by this example of a trajectory that leaves the domains. And this is also true for beta equals 0. Now, what happened? And wait, when beta equals 0, the main difference is the speed. So when beta equals 0, the speed of leaving 0 has changed. The speed of leaving 0 has changed. And indeed, you just have to integrate r dot equals r cubed to see that it's not any more exponential. So what happened when beta is negative? Then in that case, the equation beta plus r squared has a solution. It has only one positive solution, which is r equals square root of minus beta. And this corresponds to actually a limit cycle. And what is now the stability of near r equal 0? So the dynamical system can be approximated by r dot equals r beta, where beta is negative. So if beta is negative, it means that 0 is an attractor. And the limit cycle, the cycle is a repulsor. And this is well illustrated in here, where you see that 0 attracts. The limit cycle here, all trajectory that rotates around are coming from the limit cycles, while if we are outside, the trajectory goes to infinity. So I think this is remarkable and the basic example of what bifurcation is about. That is, you change the value of beta from positive real number, nothing happened, until you reach here a certain critical value where the speed of leaving or entering a critical point changes, and after crossing this point, the nature in here, the nature of the recurrent set has changed from one in here, one repulsor, to one attractor. 0 becomes an attractor, and then the limit cycles. You have a limit cycles and this attractor inside. So this is what the bifurcation theory is about, and you can consult the literature on this. There are many interesting and complete books. For example, there is books of Kuznetsov that I recommend you to read about the bifurcation of dynamical systems. This is in Springer. All right, so now I would like to give an example, and this is really not part of, this is an exercise I would like to give you. So now we are considering a dynamical system which has to do with depression for neuronal activity in that you can use to model the dynamics of the voltage of the neurons, where V is voltage and mu is called the depression variable. And so it turned out that, and we will discuss that later on in the class, that if tau here is a constant, capital U is also a constant, and TR is a constant. Now, let's suppose we don't have an injected current. Suppose you don't have noise. So you have just a dynamical system, which is V dot multiplied by tau equal minus V plus mu U. So WT will be the parameter of our system. That is something that can change. And R of V is a solution of this. This is just a simple function, which is 0 if V is less than T, and then just linear with the slope alpha. This is alpha V minus T. So now suppose you have this dynamical system which becomes now a deterministic system. Can you draw the phase space? I want to give here something that is not routine, but something that you have to look at this carefully. So can you draw the phase space? So let me help you a bit on this. So again, this is not here. So for this, you'll have to look at the critical point, V dot equals 0, and then you go also to mu dot equals 0. And then the idea is to specifically look at the number of zeros. If you look at mu, let's say, as W2 is varying, what's going to be the solution, the number of solution for this? All right, and I'll summarize this. I will continue in the next class.